Uh, Good morning, students. I am actually this time making a video. It is first for review of integration. My aim is to make some videos on this differential equations, beta gamma function, and other concepts where you have the use of differentiation. Actually, this video will go to undergraduate classes and BTech engineering. You know, as per the syllabus of University Grants Commission is concerned, your syllabus after 12th class, when you join, some of you join this undergraduate classes and some BTech engineering classes. There you have the concept of in some modules you have concept of differentiation, higher differentiation, and in some cases you have concept of higher integration. Some of the students were telling me that we are not following the concept of differential equations fully. We have some problems in differential equation, double integration, triple integration, beta gamma functions. You have power series, you have Laplace transformation, you have Fourier series. All these depend on one concept. It is your integration. Actually, you did this integration in your previous class, I mean 12th class, or in your entrances classes. But the fact is, some students were telling that we are not following it. The reason is you have kept this integration concept in your subconscious mind, unconscious mind, when previously it was in I want to just bring it first to your integration concept. That is, I will be teaching you first a review, or it is the basics of integration. I want to give you the basic concept of integration. You will be using it then differential solution of ordinary differential equations, solution of ordinary differential equations, how to solve partial differential equations, and how to solve this beta gamma function, and you have Laplace transformation, Fourier series. There are so many things which depend on this integration. Integration is the pivot around which this whole revolves. So, to give you the basics of this integration, why not to first give you the definition of this integration? Let me define definition of integration. What does integration actually means? Well, you know, you are using this integration through the concept of differential calculus. Whosoever among you has the differential concept very strong, he can tackle the integration very easily. He can solve the integrals very easily once you have the concept of differentiation fully occupied with concept of differentiation. Then this integration is applicable in many fields: ordinary differential equations, partial differential equations, beta gamma function, and this double integration, triple integration, and so on. But before this, I want to tell you, you actually do the integration through differentiation. Some of you may be saying that it was the differentiation that came first, and after differentiation you have the concept of integration. But it is not so. The origin, if we talk of origin of integration, It is even before the principle of Archimedes, even before 17th century, when it was given by Isaac Newton and Leibniz. They developed the concept of differentiation. Then what we did, we applied differential equation, differentiation in solving the integrals. Means this work became very easily when the concept of differentiation. What I was telling you, that before differentiation we had the integration. How? Suppose we have to find out the area of any curve like this. You would go like this. You want to find out the area of this from A to B, this area. Before differentiation, we used the concept of integration. We use it to find the integral from A to B. Which you have already done this in your class 12th. That is limit of the sum for finding out the area using integration. That was the first concept, fundamental theorem of this integral calculus. We say that is the fundamental theorem of integral calculus. But when we have the concept of differentiation, we use this differentiation to tackle the problems of integration. Otherwise, origin of integration is before than that of the what? This differentiation, integration. So this is clear to you that we will be now dealing with this differentiation, this concept of integration through differentiation. So on the basis of this, we define this. Definition is this: integration is what? Is the process of finding out a function whose differential coefficient is given. You might have come across such definitions in your previous class, higher secondary part 2, which we say that 12th class. You might have done it there, that it is the process of finding out a function whose differential coefficient is given. Some authors define it as the reverse process of integration, is the reverse process of differentiation. That is also in some way correct. Well, what does this mean? A process of finding out a function whose differential coefficient is given. I will give you a little bit idea, because this is for higher, not 12th class, that I said earlier. Suppose I have to find out integral of fx dx. This function fx, it is differential coefficient of some function. Differential coefficient of some function which we want to find out. It is also known as, this is also known as integrand. We sometimes also say it is an integrand. So what is the integrand which we have to integrate? Integral of fx dx. This fx is what? It is a differential coefficient of some function, and we want to find out that function. What is that function? For example, you have integral of n x raised to power n minus 1 dx. Okay, you have this integral of n x raised to power n minus 1 dx. You know this n x raised to power n minus 1, it is the differential coefficient of what? X raised to power n. So we can write it is what? X raised to power n. This is the concept. There you write also plus c. This c is clear to you from your 12th class and previous classes. This is the constant of integration. This is the constant of integration, but we use only in case of indefinite integration, not indefinite. It is indefinite. Definite, you will remember, definite means when you have limit, say a to b, it is a definite, its value is definite. But here when you don't have the limit, you use the constant of integration c. And you have also come to know from your previous classes why this c we can write. Sometimes you can write c1, c2, it is arbitrarily constant, it is not known, it is arbitrarily constant, you can use it. Well, the fact is, on the basis of this, we can have the now formula which you have also done in previous class. Suppose you have now integral of x raised to power n dx. I can write it now. It is x raised to power n plus 1 by n plus 1 plus c. Why? Because if I differentiate this x raised to power n plus 1 by n plus 1 with respect to x, you know this will be nothing other than x raised to power n. So integral of this is this. Do you follow? But it is not, this integral does not converge. Where? For n is equal to minus 1. N should not be minus 1. If we take n is equal to minus 1, it becomes undefined. It is not defined for n is equal to minus 1. This is the first fundamental formula that you did in your previous class. Well, this is your let us see. You can now ask me if n is minus 1. For example, you have integral of x raised to power minus 1 dx. What is this? Because we took here n1, now minus 1. This is as 1 by x dx. And you know 1 by x is derivative of log x, log of x to the base e. It is log x. So you can write now it is log of x. It is known to the base e plus c. So you have fundamental formulae on integration. It is just, I told you, it is review. It is the basics of your integration, what you previously did. So on the basis of this, you may have integral of ax plus b raised to power n dx. You will remember this. It is your ax plus b raised to power n plus 1 by internal derivative of this ax plus b, that is a, write a this power n plus 1. Why so? If we differentiate this with respect to x, we get this thing. Okay, this is plus c, constant of integration. Similarly, you have, you know, derivative of sin x with respect to x, derivative of sin x with respect to x, you know it is cos x. So on the basis of this, you can say integral of cos x with respect to x is now sin x plus c. You know derivative of cos x with respect to x is minus sin x. So this means if I take this minus in this side, I can write derivative of minus cos x with respect to x is sin x. Doesn't this mean integral of sin of x with respect to x will be minus cos x plus c? Is it? You have the, from lower classes, differentiation of tan x with respect to x. You have secant square x. So you can write integral of sec square x dx is tan x, constant of integration c. Similarly, you have derivative of cot x with respect to x is minus cosec square x. You take minus this side, you can write derivative of minus cot x with respect to x is cosec square. So that means that integral of cosec square x dx will be minus cot x plus c. Okay, this is just your basic of this. Now, next we take inverse functions. You have derivative of sine inverse x dx. You know it is 1 by under root of 1 minus x square. and you have derivative of cos inverse x with respect to x is minus 1 by under root of 1 minus x square. So on the basis of this derivative, I have the two fundamental results on integration, that is derivative of sine inverse x by a with respect to x will be 1 by under root of a square minus x square, and derivative of cos inverse x by a with respect to x will be minus 1 by 1 by under root of a square minus x square. This means I can write differentiation of sine inverse x by a with respect to x is 1 by under root of a square minus x square, and I can write differentiation of minus times cos inverse x by a with respect to x is what? Minus 1 by under root of, plus 1 by under root of a square minus x square. The same. This is same here, but only here it varies. It is here sine, it is here minus cos. So on the basis of this, I have a formula now. I have a formula now on integration, that is whenever I come across integral of dx by under root of a square minus x square, okay, a square minus x square, I can write it is now sine inverse x by a plus c, or I can write it as per my requirement. Sometimes I may have to convert it in cos. I can, according to this, I can write it minus cos inverse x by a plus c. You may use this or you may use this, okay. Similarly, you have derivative of tan inverse. Now this is your formula. You will be using this formula now. This formula, okay. You have tan inverse x by a with respect to x is, if you evaluate this, you will have this a by x square plus a square, because you know what is tan inverse x, 1 by x square, 1 by 1 plus x square. Cot inverse x derivative, cot inverse x derivative is minus 1 by 1 plus x square. So because of this a, it is a x square by a square. When you differentiate cot inverse x by a with respect to x, you see this will be minus a by x square plus a square. So I can write that 1 by a derivative of tan inverse x by a with respect to x is your 1 by x square plus a square. Here I can write it taking 1 by a here, then derivative of writing here minus cot of x by a with respect to x is again 1 by x square plus a square. Here I am observing derivative of 1 by a times tan inverse x by a dx is this, and 1 by a times derivative of minus cot inverse x by a is again this. Doesn't this mean that this gives me the formula that integral of dx by x square plus a square? If I want to convert this in terms of tan, this will be your 1 by a tan inverse x by a, or you can write the same as, according to this, minus 1 by a cot inverse x by a, okay. This is your derivative, another formula, dx by x square plus a square 1 by a tan inverse x by a minus 1 by a cot inverse x by a, integration of this. Sometimes you write this, sometimes you write this. This is the fundamental result. This is now one more fundamental. Sec inverse x, derivative of sec inverse x with respect to x, you know it is 1 by x under root of 1 minus x square. Now x times It is x square minus 1. Derivative of this. Sec inverse x. 1 by x under root of x square minus 1. If you have on the basis of this derivative of secant inverse x by a with respect to x, you will see it comes to be a by x times under root of x square minus a square. A times x by under root of this. Similarly, when you differentiate cosec inverse x by a with respect to x, you will see this is minus a by under root of x times x square minus a square. So, like previous formula, जिस तरह मैंने previously इसको connect किया था, now I can again connect this way, because if I take this a here down, this will be 1 by a secant inverse x by a is 1 by x square minus a square. If I take minus 1 by a here, it is again integrand becomes x under root of x square minus a square. So on the basis of I have a common integrand, that is integral of dx by x times under root of x square minus a square. This is equal to what? You can write it. It is 1 by a secant inverse x by a, 1 by a secant inverse x by a, or you can write the same, minus 1 by a cosecant inverse x by a. Then you have another one more fundamental formula. This is another fundamental formula that will be using in future. You will remember dx by, for 12th class students, we don't do there directly, we deduce this one. Actually you take here mod. This when you write integral of sine inverse x with respect to x, that comes to be 1 by mod x under root of 1 minus, because there we are dealing with the real, there is a range there. A range is the range of sine and cos we use there. In any way, this is dx by x under x square minus a square. We can write it 1 by a secant inverse x by a. If I in differential equations, solution of differential equations, sometimes I need the result of this in terms of cosec inverse. I can write in that way. It is minus 1 by a cosec inverse x by a. So up to this you have what is the derivative of this, the derivative, this integral of this is this. Okay. So you have come to know tan inverse. What is derivative of tan inverse x? Integral of integral of tan inverse, cot inverse. We have converted it. It is integral. Then similarly sec inverse, cosec inverse. Then you have next. Let us now take hyperbolic functions. Hyperbolic functions. These functions always come across when we are in undergraduate courses or we are teaching BTech mathematics students. There you have this. I will just define what this actually this hyperbolic function mean. Then you will remember what is the integral of this hyperbolic function. What is this? It is actually sine hyperbolic of x. It is not sine, it is sin. We write it shine. Sine hyperbolic or shine. What is this equal to? It is e raised to power x minus e raised power minus x by 2. Similarly, you have cos hyperbolic, cos of x. What is this? It is e raised power x plus e raised power minus x by 2. You just remember this. Okay. You see, if I differentiate this, if I now differentiate sine x with respect to x, sine hyperbolic with respect to x, it will be derivative of this. It is e raised power x. Derivative of this, you know, it is e raised power minus x, as it is differentiation of power, that is minus 1. It makes it plus. It is plus e raised power minus x by 2. What is this then? This is cos x. Okay. Derivative of sine comes directly cos. Similarly, derivative of cos x with respect to x will be e raised power x minus e raised power minus x by 2, that is sine x. And you have no change here, just like you write integral of sine with respect to x is minus cos, integral of cos with respect to x is sine. But in this case, no. In this case there is no negative sign. So how you will remember? You will remember now integral of sine hyperbolic of x, sine x with respect to x is what? It is directly cos x plus c. And integral of cos x, cos hyperbolic of x, it is directly sine x plus c. Derivative of integral of sine, cos, integral of cos is sine, no minus sign there. Okay, this is something review. I am just taking you to take the integration from your subconscious level to the conscious level. You did it already in your previous classes. So when you are very much equipped with this integration, you can tackle many problems in ordinary differential equation. Then you have the Clairaut's form there, you have the exact differential equations, you have the Bernoulli's differential equations, you have the solution for P differential equations, you will come across there. You have the double integration, you have triple integration, you have beta gamma function, you have so many concepts that we have to deal in higher classes, but all those depend upon your concept of integration. So some students from JK State, from our area, were saying me, we are not following this in our undergraduate courses or BTech classes directly, this differential equations, although they did it in your 12th classes, they did there. But the fact is, you have actually forgotten this concept of basic concepts of integration. Once basic concepts of integration are clear to you, you can directly apply them in any of the results that you will come across in future in your you have first two modules linear algebra, then you have this differential equations, so on and so forth. I will share with you about 2 or 3 lectures on the basis of this integration. I will give one or two lectures more on the basis of this integration, and then I will take you how to solve ordinary differential equations, partial differential equations, many things, but using the tool in your hand. It is the concept of integral calculus, and there is no harm in it. You have done these things in previous classes. We are just reviewing it. When you review it, when you get the basic back, then you can apply these in your future classes. So by that I will stop here. I will try to give this will be basics of integration in my video number 1, lecture first on basics of integration. Then I will give you second lecture again on the basics of integration. Thank you. We will meet again in next lecture. Thank you.